All right, kiddos, let's try to get some understanding as far as how we find the instantaneous rate of change of a curve at a point. Okay, we're talking about how we find the rate at which something is changing at an instant, which is quite remarkable. So what we do, as you recall today, is we start with the average rate of change. And so the notation we've used is on a function, the average rate of change between 2 points, right? And the 2 points we're going to call A and f of A, and A plus H, f of A plus H. Okay, those are the 2 points. To find the average rate of change, we're going to find the slope of the secant line, the slope of that line that connects those 2 points on a curve. Okay, so the slope of this guy right here, this secant line right here, between the point A, f of A, and A plus H, f of A plus H, is going to be the average rate of change of this function between these 2 points. All right, and so what I'm going to do is instead of x's, I'm going to use a, so I'm going to work up here. So the average rate of change from a to a plus h is the slope of that secant line, which is a change in y, which is going to be f of a plus h minus f of a, all over a plus h minus a. That's a change of x. A plus h minus a, and of course that leaves us just with an h. Okay, so this guy right here, this is the average rate of change, the slope of this secant line. Okay? It's the rate at which this function is changing between x equals a and x equals a plus h. Average rate. All right? Not an entirely interesting idea. However, it does become interesting when I think of, well, what is the instantaneous rate of change of the function at a point? Okay? So this is really what I'm looking for. Okay? The slope of this tangent line at that point. Okay, so the average rate of change, the instantaneous rate of change of this function, right, at this point, x equals a, is also the same as the slope of that tangent line at that point. Okay, and so the question is, well, how do we find the slope of that tangent line? Well, we start with the average rate of change, right, the slope of the secant. Okay, we start right here, this difference quotient, which just is the same as this guy right here, the average rate of change between these 2 points. And what I'm going to do, however, to turn the average rate of change into the instantaneous rate of change at A, is I'm going to pull these 2 points together. How close? Wicked close. Okay? The slope of this secant line is the average rate of change between these 2 points. The slope of this tangent line is the slope of the function at x equals a, the instantaneous rate of change. Right? Average rate of change, slope of the secant line. Instantaneous rate of change, slope of the tangent line at A. Okay? So the only question is, well, we're still evaluating the slope, rates of changes, but by bringing h to 0, I'm bringing the point A plus h arbitrarily close to A. Okay? So that really I'm evaluating the slope here, but it's between 2 points that are very, very, very wicked close together. Okay, therefore giving me the slope of the tangent, or the instantaneous rate of change at that point. Okay, so it's really a very interesting, neat idea. Okay, so to find the instantaneous rate of change, this here is what we're going to use. Okay, slope of the tangent line at a point, instantaneous rate of change of the function at that point. Okay, we're just going to start with 2 points, bring them wicked close together, evaluate the slope between them. That's the instantaneous rate of change at that point, i.e., slope of the tangent at that point. Okay, let's look at an example. Okay, and we'll start with some basic algebraic examples, just so we understand the concepts. Okay, number 1. What is the slope of the tangent line, m for slope, sub t for tangent, or instantaneous rate of change of the function, let's do x squared at x equals 1. Okay, so what I'm going to do is I'm going to create a graph. Here's part of the x squared function. Here's the other piece right here. And here's the point 1 here. So I'm going to call that point, actually I'm going to make that point red. Okay, so that's what I'm looking for, the slope of the tangent at that point. All right? So how do I get the slope of that tangent, which I actually want the tangent line to be red? I want the slope of that guy, instantaneous rate of change at 1. Well, what I'm going to do is I'm going to start with the slope of the secant line. the average rate of change. Okay, I'm going to start with 2 points on the curve. 1 and then 1 squared, which is 1. And then a point after 1. So I'll call it 1 plus h, and then the quantity 1 plus h squared, because it's going into the squared function. Okay? So now the slope of the secant line, average rate of change, is going to be the difference quotient, the change in y, which is 1 plus h squared minus 1 all over the change of x. 1 plus h minus 1, which is just h. Now, as that stands, that's the average rate of change between these 2 points. But that ain't good enough. I want the instantaneous rate of change, the slope of the tangent. So what I'm going to do is I'm going to drag the point 1 plus h closer and closer and closer and closer and closer and closer, and continue to evaluate the slope between those two now wicked close points. How do I get those 2 points to be wicked close? I take the limit as h is going to 0. And as h goes to 0, 1 plus h goes to 1. I'm still evaluating the slope between 2 points, quote unquote, but they're wicked close together. Okay, from here on out, we can calculate this limit pretty easily. I'm going to multiply out. All right, I'm going to expand the 1 plus h squared, bring down the minus 1 all over h, and just as we have talked about in the past, nice things will happen, right? And so I get limit as h is going to 0 of 2h plus h squared all over h, which you can pull an h out of everything, right? And now I substitute and 0 in for h. Okay. Oh. So we end up with 2. Okay. So the answer to this question is 2. Meaning the slope of this tangent line, 2y equals x squared at 1 is 2. Okay, that's the instantaneous rate of change of the square function at x equals 1. Okay, note how I'm using this limit process, right? And using the limit as h is going to 0 of f of a plus h minus f of a all over h. That's a difference quotient. The limit brings the 2 points wicked close together. Give you the slope of the tangent, the instantaneous rate of change. Okay, the 2 questions I would like for you to consider are here as follows. Find the slope of the tangent y equals 3x squared at x equals 1. And find the instantaneous rate of change y equals 3x squared at x equals 2. Okay, we'll go over the solutions for this tomorrow in class. Have a great day.